So have you actually come up with a number for any of them?
Well,
Actually, you can tell me. So what were the patterns you realized?
well, for like number one, it's 1/1 squared plus 1/2 squared plus 1/4 squared plus 1/8 squared, and so on.
But there are some minus signs in there, right?
Oh, okay.
Right.
Um,
But yeah, that's true.
okay. And then for like number two, it's just each number, um, like n plus one times m plus one or something like that, right?
Yeah, great. So you notice the numbers on the bottom each differ by 2, so it's 1 over n plus 1 times n plus 3, added over and over, right?
Okay, yeah.
Yeah. So I guess we'll start with that one for now. So whenever you see something like that, 1 over n plus 1 times n plus 3 all in the denominator, a lot of times where those come from are some kind of derivative where you take derivatives and then you you integrate, right? Because that's where you get those expressions involving n on the denominator. So maybe you start out with some series, you integrate, and then you multiply by some power of x and integrate again, stuff like that. So integration is what gives you extra powers in the denominator. And the reason those might differ is maybe you multiply by x squared in between or x in between and then integrate. Hopefully you can see where I'm going a little bit with that.
Yeah.
But yeah, so if you want, you could try right now to find out what series what common Maclaurin series you do some combination of those operations to get, if you'd like. And then obviously it's not a Maclaurin series, so you're evaluating this at some number, of course, for all of these. But that's what a lot of these come down to. Is there some kind of derivative or integral or a combination of taking derivatives and multiplying by x, or integrals and multiplying by x in some order of a common Maclaurin series where you just plug in a number. So you just want to find out what that function is that's behind the scenes. A lot of the times it's just 1 over 1 minus x, right? Because then that number is just the sum of x to the n. And then, like I say, you do this integration, derivatives, multiplying by x, all that stuff. And then so since you can do that to the series, once you know what you're doing, what Maclaurin series you're starting with, that's a function, right? Like 1 over 1 minus x. And you know the steps are, I'm not talking about this one, but multiply by x squared and then integrate, or multiply by x and then integrate, or just take the derivative. Once you know what you're doing and you know what that starting function was, and you have to figure out what you're evaluating. A lot of times it's 1. Once you know that, you can do that to the actual function. So if it's like 1 over 1 minus x, and you know the steps were multiply by x and integrate, or maybe the steps were take the derivative, you just do that to that function, and then this is that evaluated at some number. That's what a lot of these are.
Okay, so when it says evaluate the following sums, it wants me to come up with like a power or a geometric series or something like that, right?
Geometric series. So
Or power series.
I don't think any of these are simple geometric series, because those is just, the sum of, each term is the previous term multiplied by something. A lot of these are a little bit more complicated. So they're like, I told you, they come from Maclaurin series, like 1 over 1 minus x, or some other ones are e to the x. Those have Maclaurin series you can recognize, like e to the x is, do you know what that is?
No.
It's the sum of x over n factorial. So they're all from like a little more complicated functions like that. Like you see in number 4, you have those n factorials on the bottom. So that looks like it came from e to the x. And then sometimes you'll see, like I say, these numbers on the numerators. Like if you look at number 4, a lot of times those come from taking the derivative, right? Because if you, e to the x is x to the n over n factorial, but you can look these up. But so when you see numbers appearing on the top that you don't expect, those are usually from taking the derivatives, right? Because say you have x to the n over n factorial, and then you take the derivative, I think you might get that, but hopefully you see what I'm saying. That's where the 2 comes from, right? Do you want to, let's go through a simpler example, because I don't want to give you the answers to these specific ones, but like if I gave you a series which was the sum of, well, let's just go through it forwards. So like e to the x is the sum of x to the n over n factorial. And then if I take the derivative of that as a series, what do I get?
1 over x to the n factorial?
It's x to the n over n factorial. Or actually, sorry, can I give you another example? Sorry, I hope I'm not jumping around too much, but this isn't a good example because when you take the derivative of it, you get itself back. So that's really bad to illustrate this principle. But so 1 over 1 minus x is just the sum of x to the n. And you have to worry about whether you're indexing starting at 0 or 1, but for now, let's not think about that. So this is valid for x between -1 and 1. Anyway, so so a lot of times, like for these series, you're usually plugging in 1/2 for x, or it's sometimes just 1. But anyway, yeah, sorry, and this, yeah, so I think this is valid at 1 also. You would have to double check. But anyway, so if you have this and you take the derivative, you get, this is where you'll start to see these numerators show up out of nowhere, kind of. You get the sum of nx to the n minus 1. See? Okay, and then if I evaluated that at 1/2, right, and then if I evaluate that at 1/2, sorry, I hope you can see, I get this, and then just to make that a little clearer, to write those out in just some numbers, you get 1 plus, sorry, 1 second, so let's see. I'm going to say this starts from n equals 1 to infinity, right, because took the derivative, we lost a term. I don't want to get too down in the weeds here. I want to stay in the big picture. But anyway, the point is you get these. So you get some of these terms, right? So you can see there's like these numerators pop out front, just like in number 4. Do you see kind of the connection there? I'm not saying like, do you know how to solve that problem, but I'm just trying to show you how when you take the derivative out, you get this pattern where the numerators change, right? So like you have 1 is in the numerator, but then you have 2, 3. This should hopefully make it clearer. So right here, you can see how this 1, 2, 3, 4 comes out in the numerator. That all comes from taking the derivatives, right? Because in a Maclaurin series, it's all some coefficient, some coefficient times x to the n, and when you take the derivative, that n comes down. So that's where this comes from.
Okay, I'm a little embarrassed because I'm having a hard time following. This is my first graduate course, and I'm 33 years old, and I haven't taken school in a while.
Oh, I'm sorry. Please don't be embarrassed. I'm a little older too. I'm 26, and I'm gonna start grad school hopefully next year. So okay. I feel you. Yeah. Okay.
This is a course called Math Methods for Scientists and Engineers, and it's like an amalgamation of different calculus and linear algebra and differential equations courses and stuff like that.
Okay.
And
okay.
This week we're doing infinite series, and I'm just so lost.
Okay. Well, why don't So okay. So if you're lost, why don't we start with some of the simpler ones? Because some of these are really complicated, actually. So why don't we start with number 1? Or we could start with some even simpler ones. Well, let's start with number 1. They're tricky, is what they are. Okay, so please stop me and ask questions. That's what this is for. But number 1.
Would have anything to do with like cosine and sine, because you can get like cosine negative derivative of cosine is like negative sine, right? And then derivative of negative sine is negative cosine still, so you have 2 negatives in a row, and then you're back to sine, which would be positive. And then
I see where you're coming from. It's funny, I had kind of the same thought too. But when I looked it up, this is a little embarrassing. I looked it up online because I knew there was some trick I'm forgetting. these kinds of things with the double minus and double plus, they're usually two series written together. So really, yeah, I was kind of embarrassed I forgot that trick because that's a big one. So yeah, I knew there was something I was missing. So if you look here, this is really two series added together, right? It's 1 minus 1/16 plus 1 over 256. I'm just taking the first one of each of these pairs and putting it in a series, and then I'm taking the second one and putting it in a series. Because the thing is, for any of these series, you really never see that pattern. It's either kind of all plus, all minus, or plus minus, plus minus. So this is really weird, and that's just because it's two added together.
Okay.
So that's good to remember. Okay, and like you say, so so now that we have it, and now we've reduced it to just finding what S is, right? So let's just focus in on this. Like you notice, these are powers of 4. So we have S is 1 plus, S equals 1 minus 1/16 plus 1 over 256. And that's just 1 minus 1 over 4 squared plus 1 over, I think it's 4 to the 4th, maybe? Is that right? Or is it 4 cubed? I think it's 4 cubed. Let's see.
4 cubed is 64, right?
Yeah. So then it's 4 to the 4th. Okay. And then it's going to go on like that to 4 to the, let's see, the next one, would it be 4 to the 6th? Well, you can take your time too and do this too.
Yeah.
Because that matters, right? We're not, from here, I'm not sure if it's 4 to the 8th or 4 to the 6th. So let's look at these denominators. So just ignoring the plus and minuses, I want to see what these are. 4 to the 1st, 4 squared, 4 to the 4th, 4 squared, 4 cubed, 4 to the 4th, and this is that times 4, right? 4 to the 5th. So yeah, the next one's going to be 4 to the 6th.
Yeah.
Okay.
Yeah, and
then plus 1 over 4 to the 8th. So the point is, I'm going to write this in a little easier way because it's really something else that's even simpler. It's 1, instead of the thing being 4, it's 4 squared, right? And then it's just the powers are just, really easy. Let's see. So this series that shows up a lot, which is just things like some power, like the sum of x to the n, that shows up over and over. And that's a function that we know. Okay. So, yeah, let's see. So if you just realize this, if you realize that this 4 squared is a real thing, you see you have 1 minus x squared plus x, did I write that wrong? Yeah, this is 1 minus x plus x squared minus x cubed plus x to the 4th. So that's something we recognize more. So are you used to seeing like the series 1 over 1 minus x is just x to the n, that sum? Have you heard of that?
I'm sure I have, but
okay. Yeah. So anyway, this is a little different because the terms are alternating, and where that comes from is just there's a minus sign somewhere instead. So 1 over 1 minus x is the sum of x to the n, but 1 over 1 plus x is this alternating one. So that's what this is coming from. Yeah.
So would you write that with like a comma?
Write that what?
With like a comma, like this one, comma that one, or would you try?
It doesn't matter how you write it. So I'm just trying to show you how you find out what the number is, because at the end of the day, I mean, they probably do want you to show work, but I wouldn't worry about that too much. Just focus on understanding the stuff. So the point is, we know that this series is this, right? S is still S. It's this, right? 1 minus x plus x squared minus x cubed plus x to the fourth, and so on. Now we know what that is, right? And it's evaluated at 1 over 4 squared. We just have to keep noticing these patterns like you did. 1 over 1 plus x evaluated at x equals 1 over 4 squared. So let me know what you think of that so far. And
I'm sorry, a little lost. 1 over 1 plus x evaluated at x equals 1 over 4 squared.
Yeah.
And what does that come to?
So you just actually evaluate it. That's how these usually work. 1 over 1 plus. So that's some number, right? It's like a fraction. You actually.
Oh, okay. Evaluated at. Okay, I understand.
Yeah. So that's how you actually solve all of these, pretty much. Some weird variant of this. Yeah, and then you can remember our original series s plus 1/4 of x.
Okay.
Mm-hmm. Do you have any questions about that one?
I'm not sure.
I'll also send you this too after, but I'm happy to talk about it more too. This is interesting. Good example.
I guess I'm just still. I'm so sorry, but I guess I'm just still lost a little bit.
Oh, that's okay. So yeah, these series things are hard, especially if you haven't seen them. And these ones are really tricky ones to start with for your professor. But I guess that's what it is. Yeah.
I think
so,
he more like a review, but
what, he thought it was a review?
I think he thinks of it as like a review, but
Okay.
yeah.
Yeah. All right. So I think one thing you should do is just, have you ever heard of Maclaurin series?
Yeah, like Taylor McLaurin.
Yeah. So I would just like pull up a table of some common ones and just have them with you. That's kind of important. You could even pull it up on your web browser right now. I can send you a link. Just give me a second. Yeah, here. I'll send you this one. So I have the video in chat. Okay. Yeah, so here's this.
Okay.
Yeah, so it's good to kind of have these in mind, because then you can start to see that some of these series look like them somehow, but maybe there's just like an extra, there's like the n+3 in the denominator, or things are shifted, like instead of being 1 over n, it's 1 over n+1, things like that. But the point is, they pretty much all come from these, and like I say, and then at the end of the day, you plug in a number, like it's usually like 1 or 1/2 or something. But you can see on the right, like these patterns, they look a lot like what you were given, right?
Yes, they do. Yeah.
Yeah, in fact, right on the denominator. So I mean, you really kind of, it's weird. You don't even need to think about this precisely right away. You can just look at it and look like it's kind of like a riddle. You see like how they got from, you want to reverse engineer how they got from one of these series to, your sum. So like, let's, if you don't mind, let's go over number, what was the one with the 1 over n+1 times n+3?
That was number 2.
Yeah, okay, well that works out. So let's go over that. Like I said, so that's the one which has to do with integrating, because whenever you, so like I said, with the differentiator, you saw the ends come up on top. Here you have some extra ends come up on bottom. Okay, so like you said, this series is actually the sum over 1 times n+1 times n+3, and this looks kind of. Can I show you a similar example, which is just 1 over n times n+2?
Sure.
Okay. So this looks if it were this, if it were the sum of 1 over, oh, actually, okay, right. So the point is, how might you get an n and an n plus 2 in the denominator? That's what it comes down to whenever, like I said, is by integrating. So I'm going to go do this process forward, and then you'll see how it works. So 1 over 1 minus x, I'll send you all this too, is the sum of x to the n. And then let's say I integrate that. I'm not actually going to integrate the left side, which I will have to, but I'm just going to integrate the Taylor series term by term. So when you integrate, you get that, right?
Okay.
And then if I wanted to plug in some number, I could, right? So like if I saw a series that was like, I don't know, say we plugged in 1, right? Equals. Actually, so one thing is, let me see, were there any minus signs in there, or were they all pluses?
They are all pluses.
Okay, so one thing we need to do is we need to check. Remember I sent you that thing that says Maclaurin series?
Yeah.
We need to make sure this converges at the number we plug in, right? Because so for any series, like I can't plug in, I was thinking plugging in 1 for x, right? But that won't, like that can't converge because first of all, if you plug in 1 for x on the right, it's infinite. And same on the left. So I mean, they are equal, but you don't say that. So you have to be a little careful that it actually converges at the point. But anyway, let's see. Hi, sorry, I'm tutoring. Sorry about that. That was kind of unprofessional. Okay. So sorry, 1 second. So actually, that won't work. I was thinking about plugging in 1, but something similar might work. So like, let's see. The point is, it comes from one of these series. Oh, this is weird. I can't see. Your PDF is closed now. On your doesn't work PDF. I'm sorry. I'm having quite a bit of technical trouble. Anyway, let's see. Sorry, 1 second. So since there's an n plus 1 here, one thing I am thinking is instead of having 1 over 1 minus x, maybe you started with 1 over 1 minus x squared, and that's where the extra 1 came from. I'm giving you my train of thought here, and maybe it's helpful to you. Maybe you started with something like that. But that wouldn't make sense because if it were 1 over 1 minus x squared, just ignore the specific problem and just try to hopefully see how I think about this, but maybe it'll help you. If you had an x squared there, then everything would have like an even power, right? It would just be wherever you have an x, you have an x squared. So it would just be the sum of this, sum over x squared to the n, which is just the sum of x to the 2n. So that's, you really do just reverse engineer these. You see, where did this slight modification come from?
Okay.
We could also look, so this is how I would actually do this
too. I added the PDF to the whiteboard.
Oh, wow, thank you. Oh, great. Let's see. Nice. Oh, okay. Yeah. So if you want, we could look at the Maclaurin series again. Oh, actually, you know what? I think this series comes down to a different technique. So using partial fractions, I think like each of these numbers is like 1 over n minus 1 over n plus 2. Like each of these numbers is actually the difference of two numbers, for instance. That's something that comes up to a lot. So hopefully we'll see where I'm going with this. Let's use my slightly different example. Let's use 1 over n times n plus 2. So that would be, we'll start at n equals 1 because it doesn't matter. You just have to think about it. 1 over 1 times 2 plus, sorry, 1 second. Oh, well, that is the same. I mean, that's the same series. It doesn't, okay. Okay, I don't want to do your problem for you, but I'll just start with this. So you notice this. 1 over 1 times 3 plus 1 over 2 times 4. what is each of these terms? I think it comes from somewhere, right? So what if you took one, just see one thing. Let me just write this a little differently. 1/3 plus 1/8 plus 1/15 plus, I'm just going to try to look at what you see 1/3 times 5. What if that were a/5 minus b/3? That kind of thing. And then you might have something else like that.
a/5 minus b/3?
Yeah, so we're not doing this, we're not solving actually just yet, but I'm just showing you that I'm pretty sure this is where this comes from. And then this is actually a difference of two other terms, like a different a/4 minus b/2, this kind of thing. So it's probably actually something like that. I'm sorry, the bad order. Please try to not worry about the specific letters, but just see the approach. So we have something like this. Wait 1 second. Oh, this is also, wait, something weird. So, okay, so the 3 shows up in the first term and the third term, right? Because in the first one it shows up as n plus 2, and then when it shows up the second time, it's just the n plus 1.
Versus the n, right?
Yeah. Yeah, because there is like a well-known something like this. I thought that's what this was. There was one that was like the sum of -1 to the n over n. So that is just, it's this. So this is just, I'm telling you the example I've heard that seems a lot like this. Is this, let's see. Okay, so one thing I've seen is something like this. Okay, but then so this is what it is, and it's a function that I'll tell you later, but then sometimes people will disguise it and they'll combine these terms, just like this. So, it'll be -4/3 plus, sorry, -3/2 minus 1/12 minus, you're just like coupling the two terms next to each other, minus, let me write this in a slightly better way. So a lot of times, so then sometimes people will group terms in the series and it'll show up like this. Yeah. So then you can see that these numbers show up together, right?
Okay, yeah.
So maybe they did that here, but they probably did, but they grouped them a little differently, right? Because the numbers show up twice. Like the 3 shows up in the first one and the third one. Another thing we could do, so you mentioned sine and cosine. So this could look a little bit like that, because if you look at those, the sine and cosine, you have these, oh, okay, actually, let's look at our Maclaurin series. Like I said, it's one of these functions in the background. So the sine and cosine have factorials on the bottom. This definitely doesn't have that. So this probably didn't come from that, although, like I said, you can do weird things that obscure it, like what I just did. But something that this has just like something in terms of n on the bottom, right? So you want to look at those. I'm looking at the Maclaurin table I gave you. So let's see. ln of 1 plus x looks pretty good so far, right? Because there's an n on the bottom, and if we multiplied it by x first, so if we looked at, okay, sorry, let me pause there. So how do you get ln of 1 plus x from 1 over 1 plus x? You integrate, right?
Right, yeah.
And that's where that n came from in the denominator. So, but what you could do before integrating is you could multiply by x first, right? And that would get that power of n up to n plus 1. So that might be what they did. So if you look at the integral of x over 1 minus x dx, that would be negative 1. The negative doesn't change, right? That doesn't, because multiplying by x won't change that. So the n plus 1 over n plus 1. Right, so that's there. Okay. So we have that. Now, how could we, and so what we're going to do at the end of the day is plug in 1, I think. But then how do we, I'm going back to the way we have it written, right, of course, is 1 over n plus 1 times n plus 3. So how could you get an n plus 3 now, I'll ask you.
I mean, I would just, at a risk of sounding stupid, I would say just adding 3, but.
Oh, no, that's okay. But no, so the way we got the n plus 1, right, is that this series had an n plus 1 in the x, and then when we integrate, it shows up in the denominator. So what you would want to do is multiply by x squared and then integrate again. Let me write this out, though. I think I compressed it too much. So let's see. 1 over 1 minus x is this. Oh, I'm sorry. It should be a plus, but just, sorry. Bear with me a second. 1 over 1 plus x is this. Okay, so that's that. And then, like I say, we're going to multiply by x. We know if we integrate, we'll get n in the denominator, but we want n plus 1. So we want those numbers, the powers to actually be n plus 1, right? So do you see how I got from that step to that one, hopefully? Between these two?
Right, yeah.
Okay, and then you integrate. I'm not actually going to do it on the left, but I'll just know it's what happens when you integrate the right term by term. Oh, wait a second. So when you integrate, the power above goes up by 1. That's fine. And then you divide by it too, right? So actually, we didn't have to multiply by x. The reason they have x to the n over n is because they start indexing at 1. But it actually, the n plus 1 comes out naturally anyway, so I hope you don't hate me too much if I erase this and just make it a little easier. You'll see what I'm saying in a second. 1 plus infinity. See. Okay, so yeah, I made it more complicated than it had to be. I didn't see they started at 1, but if you start at 0, this n plus 1's there naturally, right, when you integrate.
Right, 0 plus 1.
Okay, and then so now we want to get an n plus 3. So the way we're going to do that is we're going to multiply by x squared, because then the power will be up to n plus 3, right? So let's do that. Okay. we do it on both sides, but we don't actually evaluate on the left thing. Sorry, actually, I'm deciding if we want to multiply by x squared or by x. We just want to multiply by x, right? It's kind of the thing I did before one more time. Sorry about that. But you can think through this stuff too. Okay, so I just multiplied by x on both sides, right? Hopefully, can you see the paper? I hope it's clear, the video.
I'm having a little trouble, but I can see it.
Okay, so it's just this line and this line. I just multiplied by x on both sides, and see now this, I didn't integrate again yet, but I will. But now this power is, do you see, does it say n plus 2? I hope I wrote it right.
N plus 2, okay.
And then remember, it's going to go up when we integrate again. So, okay. Let's see. Let's see if can you see that there? I'm not sure I'm supposed to hold it to the computer. I don't know if it focuses. Just let me know. I can hold it closer or further away if the focusing is off.
Can you hold a little closer if you don't mind?
Mm-hmm. Sure. So the whole goal here is I'm just trying to get to a Maclaurin series from some function I know to something with this n plus 1, n plus 3 on the bottom, which is what we did. We finally got to that. And now we can actually write down what this is. It's not nearly as complicated as it looks because you already told me we know what the integral of 1 over 1 plus x is. But you can look at this for a while longer if you need to. Then we can get into that. You know.
Okay.
Yeah, so that was just the whole goal of all this, was getting this. Now, what's the integral of 1 over 1 plus x? Just, you can ignore the outside. Just the inside stuff.
That natural log of 1 plus x?
Yep. Right, and that's this series, okay. Right, and then I probably won't do it here with you. Do you feel comfortable with integration?
Yeah.
Okay, yeah, so this would probably be by parts or something. But so then you integrate this and you get some function. I'm just going to call it f. It's f of x is this, and it's this series still, right? These are all equalities. And then you notice if you plug in 1 for this, I think we get what we want. We are doing that. Oh, you know what? They're all pluses, though, aren't they? I'm sorry about that. Were they all pluses in the series that you were given?
Yeah, they're all pluses.
Okay, then that's fine. But wherever I wrote 1 over 1 plus x, it should be like a minus. And then you might have to be careful when you integrate too. Hopefully you were okay with these steps because some of the integration will change, right, if you have a minus with the x. But wherever I used a 1 over 1 plus x, it should just be a minus because that's, if you have 1 over 1 minus x, the series is x to the n. Sorry, do you feel okay with what I just said there about the 1 over 1 minus x versus 1 over 1 plus x?
I assume I could play it out.
Yeah, right. So yeah, these are good to know though. Most series will go from this. Right, yeah, you can figure it out. So the point is, sorry about that, I feel bad at the computer. We should have used this one because there's no minus in front, not that one. Okay, right, and then you do have to make sure, so like I say, at the end of the day, you'll have this function here, which is the integral of this, and then you'll probably plug in something here, maybe it's 1 or something, but whatever you get, you have to make sure these series we use in each step, or at least what we use at the end, were something where you could plug in 1. like for 1 over 1 minus x, but look at the Maclaurin series picture I gave you again, the link I sent you. So 1 over 1 minus x, if you plug in x is 50, this won't converge, right? The right hand will be infinite. And the left hand won't be, but this is just wrong, this equality. So you have to make sure you're plugging in a legal number.
Okay, that has to be less than 1, right?
Yeah, you also need to check sometimes with these with the endpoints, because I think for a lot of the ones you're given, you might actually need like an endpoint where it converges. So a lot of times you plug in 1. You'll notice that when you actually find out what these series are. And you have to make sure it converges at 1. And sometimes the radius of convergence is 1, but it converges at that endpoint. Like I know, I think I should have sent you a more specific table. Like I know ln, oh, here's, yeah, this is beautiful. So these tell you the endpoints too, so you don't have to go through that again. Yeah. Okay, so ln 1 plus x is this, and then ln of 1 minus x. Can you see the yellow picture I sent you?
Yes.
Yeah, so you can do this too on your own, but I look like you find one. ln of 1 minus x converges if it's the one on the left is the on the right is the less than. So you do need to know that stuff, because I think you might need to use it. Not have it memorized, but just you need to look it up.
Right.
Yeah, and for when checking convergence, I mean, obviously you don't need to check that 1 over 1 minus x converges, that whatever thing you're plugging in, x equals 1 or x equals -1. It's important that whatever function at the end you get. So here they did the integration, right, for ln of 1 plus x. And if I had plugged in at the beginning, it's a weird glitch. I don't know why mathematically it works. If I had asked, will this converge at 1? The answer is no, right? And if I integrate, it converges at 1. So try to do it all in one step, find out what your series is, and then plug it in at the end. You don't need to look at each intermediate step. But hopefully that won't be an issue, just, checking where it converges. Okay. Do you have any questions, or do you want to move on to me giving you some more approaches for the next few?
I'm sorry, you're breaking up there. What were you saying?
Oh, sorry. I was saying, do you have any more questions about this one, or do you want to keep going on and I'll keep giving you more techniques for 3 through 7? The rest are easier. That was a tricky one. Or some of them are easier, like 5 through 7 are even easier than all the rest of them, I think. So yeah, it's not too overwhelming. But do you want to keep talking about this one or move on?
I think I'm good. I just gotta kind of plug away now. I think you gave me some tools I can use.
Okay, yeah, that's great. And if you have some more questions, I think you understand it too. But if you do have lingering questions, you can message me on the app. I think you'll be fine.
Yeah, we'll take it. Really appreciate your time.
Oh, okay. Yeah, sure, no problem. But there's one that's really tricky. So 4 through 7, I think, are totally fine. But 3 looks really tricky. I don't know how you feel about that.
At first glance, I'm trying to figure out what you could integrate to come with the pattern.
Okay. One question I have is, what are the powers on the 3s there, if you don't mind me asking?
5 times 3 squared, 7 times 3 cubed, 11 times 3 to the 5th, 13 times 3 to the 6th. And so it's a 3 to the n plus 1, but the bottom numbers are all prime numbers.
Yeah, so there are 2 separate things going on there. Right. That one's really tricky. I have a question. Is this going to be graded for you?
I'm not sure actually. We're just to do it.
Oh, okay. I'm just thinking this is a very hard problem. Okay. Yeah, so the numbers there on the bottom are the primes. And then the powers and 3s are kind of weird because there's no pattern I can see right now except the one thing I might have to say. Yeah, I'm not sure. So he writes it out with minus, minus, plus, plus. You're supposed to know the pattern, right? But what is the pattern on the 3s? I don't know. 2, 3, 5, 6. Something's so what would the next powers be is my question. Is it like 2, 3, 5, 6, what would it be, 8, 9? Do you think that's what it is?
Maybe everything that's not a well, no, because um,
So I might, you could even ask your teacher for clarification on that. It seems kind of ambiguous. I would, just to be safe, right? Because it seems like it could be two different patterns. You know what I mean? I feel like we don't
right,
have enough to go there.
right.
Are you allowed to use the internet too?
Yeah, we can use whatever we want.
Okay. Yeah, I do think you understand this stuff. So, and I don't want to, I want to discount you a little bit on this one since we had that glitch. But you can definitely email me later. And if you want, I don't have any interesting examples off the top of my head. You could look up Taylor series or series with prime numbers in the denominator, something like that. I really do think something will come up, and you might get a good feel. You'll start to see the patterns I've been showing you. I just can't come up with a good example off the top of my head, so I'm sorry about that. But
Yeah, no
you can
problem.
do that, yeah. And like I said, message me if you have any more questions.
Okay, well, thank you so much. I appreciate your time.
Thank you. Okay, great. And don't forget to rate at the end. Thank you so much.
Okay, no problem. I don't know how to exit.
I'll do it.
Okay.